Hi everyone, this video is an introduction to our reading for this week, which has 3 sections. So one of them is 4.3 on logarithms, and then the other 2 are the beginning of chapter 2, 2.1 and 2.2, talking about some basic nonlinear models, basic functions that we'll be working with all the time. So I want to talk a little bit about why we're studying logarithms now. So if you are paying attention, this is section 4.3, which we're sort of pulling in. It's out of order for the textbook from what we're doing. We have been jumping around quite a bit. So there are a few reasons we're doing it here. One is it does make sense at this point. So we've just been learning about exponents. Logarithms are the inverse functions to exponents. They're very closely related. They're very closely tied. The way they're defined is exactly from exponents. In fact, logarithms are exponents. So we'll talk about that in a minute. But also there's a pedagogical reason for pulling them in now, in addition to the fact that they are related to the current material. And that is this idea of a spiral pedagogy, which means that you're going to sort of come around and hit all the different topics and then come back around and hit them again at a deeper level, right? Or a more sophisticated level. And fun fact, I have a cousin who is in Germany in med school right now, and they're using a spiral pedagogy for med school, which is really interesting. So logarithms, why do we know? So what happens is the way we used to teach pre-calculus, we'd have all the hardest material, trig and exponents and logs at the very end of the semester. Everyone was exhausted. No one had time to learn this new material because all their classes were really busy, and there's no time to really absorb this very difficult material. And so what we did is we redesigned the course and put all the hardest material at the beginning of the semester. So you're hit with it right at the beginning. But it allows us to have basically the whole semester to really absorb and work with these really, really difficult concepts. And also to start out with them now and then come back to them at a more sophisticated level later in the semester after we've had some time to really absorb some of the basics. And there are a few different analogies. You can compare this to learning other kinds of things. So one analogy that we use a lot is the idea that learning math is very similar to learning a language in a lot of ways, that you have vocabulary you need to master before you can put them together grammatically into a sentence and express more complicated ideas. And so we're doing that now, right? We did that already with the trig, where we said, okay, we're going to learn how to evaluate these trig functions. We're going to memorize these graphs, even if we don't have a very solid understanding of where they're coming from, right? It's a hard, difficult, and abstract topic. But what it'll allow us to do is by the time, first of all, it gives us the whole semester to work on it. And also by the time we come back around to the trig at the end of the semester, you'll have all of those ideas already, like the vocabulary already memorized, so that you can put it together into more complicated ideas. And so you don't have to stop and think, wait, what does that thing mean? How do I do this? You'll already know how to do it. And the next part will be much easier for you to do. The same thing with logarithms. So logarithms, we want to learn now how to just evaluate them. It's not going to be the most exciting part of logarithms, but it will free up your head space so that when we come back to logarithms and we study the functions and the graphs and what to do with them and how they work and all this interesting stuff, we won't have to spend our brain power on just how do I evaluate it, because you'll already know how to do that so that you can move on to more things. Another analogy, you can pick anything you want, is like learning a sport, right? If you want to learn how to play soccer, you have to drill, all these basic things like dribbling the ball over and over and over again. It's not very interesting. But then when you go into a game situation, you can think about more interesting things, the strategy. Who do I want to pass the ball to? How do I get around my opponent without having to be like, wait, how do I move the ball in this direction? Because you already have that in your muscle memory, right? So it's very much like that. Okay, so logarithms, this is what we're going to be doing now at this point. It's a difficult topic because the reason I think it's difficult is because it's abstract. So compared to something like studying a function like y equals x squared, which we'll come back to in chapter 2 again also. This function is something where the formula tells you what to do. Take your number x, multiply it by itself, right? And then if you want y equals x squared plus 3, again, it tells you what to do, right? You take that number x, you multiply it by itself, and then you add on a 3 to the end of it. My internet is slow today, so it's slowly catching up. So, but logarithms are not like that. There's a notation for it that is not directly connected to what it means. And even to say what it means is kind of a mouthful. So that's why we want to practice this now and really like deeply ingrain it so that we can do more things with it later. So this is very direct. The logarithms are more abstract. It's good, logarithms are important because they're going to be important functions that we want to use to model different phenomena and that we want to study in calculus. But also, it's important for us to practice this abstraction, which is difficult because calculus, the next class up in the next level math class, is a more abstract class in general. Most of the things you're going to be doing there are more abstract than what you do in pre-calc. And so practicing that abstraction in general is also important. Okay, what are these things? So we've been studying exponents. So something like 2 cubed equals 8, right? So we've taken this number 2, we've raised it to an exponent of 3, we get the number 8. Logarithms are the inverse, okay? So a logarithm is the exponent, right, that you're raising the base to get out a number. Don't even try it. We're going to go through it. So our notation, it looks like this. So you have a new function, y equals log. There's always a base to your exponent, and the base, we try to remember, I like to think of it this way, is written as a subscript. It's the small number down below your log. Y equals log base A, so there's a little number written down here, and then there's a number that you plug into the log function. So just like sine is a function, you have to plug a number in. Cosine is a function, you have to plug a number in, right? Y equals x squared is a function, you plug a number in. Log is a function, you're going to plug the b value in. Okay, the log function, we have this notation for it, but all it is a way of rewriting this relationship with the exponents. So y equals log base A of b is the exact same mathematical statement. There's no different content from the exponential version of it, which is to take this base A, so the base of the logarithm A is also the base in your exponential version. The logarithm itself, we like to say the log is the exponent. So whatever value you get out from the log, this y value, is the exponent over here, a to the y, equals the only thing left, which is b. Okay, so a couple of things. So I've mentioned that these are inverse functions, which we'll talk more about. But if you are familiar with the idea of inverse functions, it's like the thing that I plug in here, this b, becomes the output of this function over here. The thing that I plug in here, y, is the output over here. So they're inverses in that sense, not like 1 divided by. That's reciprocal, it's different. But so there's this basic rule. So if we were going to take this same relationship, 2 cubed equals 8, and write it in the log version, right, we would have 2 cubed equals 8. We can convert it over to the log version. So the b, so let's say the y over here is the exponent. The log is the exponent. So 3 is equal to the log. The base of the exponent is also the base of the log. So that's 2. And then the number we put into the log, you can use parentheses if you want, is 8. Okay, so when we're saying what is the log base 2, so often you'll see this as a problem of what is evaluate log base 2 of 8, and you're like, okay, I have to figure out what is that number, right? And you're like, what is that number? I don't know. Of course, we know what it is. We just did it. But if we were given this problem, we say, what is the number log base 2 of 8? We would say, well, what is it? So what it is verbally describing it is, this is the exponent to which we raise the base A, which is 2 in this case. We raise the base 2 to get 8. Mathematically, we would say, okay, so this is the same as saying 2 raised to what number gives me 8, right? So the log is the exponent, right, to which we raise the base 2 in order to get the input 8. And so we see that log base 2 of 8 is equal to 3. It's the exponent that you have to raise 2 to in order to get 8. That's what the logs are, okay? And it's just a way of rewriting it. It might seem a little bit simple, like why would we do this, right? But the log functions are the inverse function. So just like we have y equals x squared and y equals square root of x, these functions undo each other. So it's nice to have both of them. They interact very nicely together. The log function sort of undoes the exponential function. That's one reason it's important. It's also important as a mathematical model in its own right, which we'll learn more about when we come back to chapter 4. Exponential growth, right, is growth very fast. Logarithms grow, they get bigger as your x values increase, but they grow slowly. So we'll talk more about that in chapter 4, but they are really, really, really important models for different phenomena that grow slowly. So it's really important to study these functions in their own right. Okay, so section 4.3, logarithms, tends to be very, very abstract. But then we'll get to take a bit of a breather and we'll go back to chapter 2, nonlinear models and some basic functions are what we're going to read for this week. These sections, sections 2.1 and sections 2.2, they're going to be more straightforward. I don't want to say easy, right? If you haven't seen it before, it's probably still going to be challenging, but like the y equals x squared example, these are functions that the formula tells you what to do. Right, so in section 2.1, we'll go back to studying quadratic functions. How do we get the roots for them? We're going to spend, there's just, I think, maybe one example in the reading of solving for variables, but this is important because in pre-calculus, one of the things, so I've asked my colleagues who teach the intro science classes again and again and again, give me, you know, they always complain, my students, they don't remember their calculus, they have trouble with their math. And I say, give me your problems, right? We'll do them in math, right? We're going to get your students ready. And when they do send me problems, the problems are always pre-calculus problems. They're never calculus problems, right? And so solving for variables, it can look really intimidating because in science, they tend to use letters that represent the quantity that you're studying, which is helpful, but it also means that there are a lot of letters and superscripts and subscripts. So we want to practice doing some of that. We'll touch a little bit on compound interest. We'll come back to that more again later in the semester. And we'll start looking at some other nonlinear functions. So we studied in chapter 1, linear functions. So these are nonlinear functions, square root of x, x cubed and cubed root of x. We'll get a little bit of introduction in section 2.1. And then section 2.2 will sort of expand that toolbox. We'll get some more basic functions. So they'll start out with an analysis of absolute value of x, which is a handy function to have in your pockets. They'll give you some examples of what functions, or they'll give you different like sort of real life phenomenon that you would model with these different kinds of functions to see why we're looking at all of these things. They're going to give you 8 basic functions. They'll look at the graphs and the asymptotes for those functions. And finally, they'll look at piecewise functions. And for section 2.2, this is the hardest thing for most people. So, piecewise functions we'll take all these basic functions that we know and use, and then we'll use different chunks of them. So I'm going to do a worked example of graphing a piecewise function, so you can check out that video to see how that's done. Enjoy the reading.